Hey guys, today I want to show you this rather simple principle called the wave-particle-duality-principle, which ultimately led to the discovery of quantum mechanics in the first place, using nothing more but this laser and the hair of mine. And yes, I think at least I can do this to my camera safely without damaging it. So let's get into the explanations. Back then it wasn't known if light, or more specifically photons, behaved as a wave or as a particle. But in 1805, Thomas Young proposed an experiment that kind of looked like this. Okay, there was a laser, an obstacle, and a screen in which you can see where the light is. So, he said, when photons were particles, it would look like what we'd expect. You know, the laser, the light goes here, and it is blocked by this thing, which means we don't have light in the middle. So it would basically look like a circle, which is lit up, but then a smaller dot in the middle where there's no light. But if photons behave like waves, it would get a little more complicated. You know, first off, in normal light sources, the light would behave like this. Those would be the points with higher amplitude. They would just go away like a circle. But in a laser, they don't. They go straight, which is why we need a laser to make this experiment. So if there were this object, the photons would split into two. By the way, the photons themselves wouldn't split, but more like the groups they were in. They would split into two groups, the one below and the one above. The one above the obstacle and the one below it, which would then look like this circle-y thing that are with natural light sources. So, and then if we had a screen there, wait, let me just make it more visible really quickly. If we had a screen there, there would be points where they would add up and where they would cancel out. The points where they would cancel out would be the half of the wavelength. What I mean by that is, if the light above would go, say this point right here, okay, and the light below it would go to this point, the light below would travel farther, and if it would travel exactly half a wavelength farther, they both would cancel out. Why is that? Because the wavelength lambda, I think, is basically this distance between the two highest points. But if now this wave came in, which was just located by 1/2 lambda, it would look like this. Do you see why they would cancel out? Yeah, they would just cancel out because, you know, for this and this point, they would add up to make 0. Okay, so we have then these dark spots, these bright spots where they add up, dark and bright and dark. You get what I mean, right? And now let's show what happens when we do exactly this experiment with this laser. So the setup is done now. There's just a hammer hanging from the wire and the laser in which a little hair of mine is. Wait, can you see it? You can kind of see it, at least a little bit. So now take your guesses. I will take a look at it now. Laser set up, and now let's go check it out. So, okay, there is the beautiful interference pattern I was talking about, so we can clearly see that light behaves like a wave. So, yeah, dispute settled. 1805, the experiment by Thomas Young. It clearly showed that light behaved like a wave, but sometimes later, about 100 years, Einstein came along. He says basically this. In 1887, it was discovered by Heinrich Herz that when you hit a metal with light, it expels electrons, okay? And so he designs another experiment. If light behaves as a wave, it shouldn't matter what frequency or what wavelength the light has, but only what the intensity of it is. But if it were particles, then it does matter which frequency it has and what wavelength. So, for example, red light has a lower frequency than blue light and a higher wavelength than blue light, because the formula given to us is c, light speed, is the frequency of a light times its wavelength. Actually pretty intuitive when you think about it, because this is just basically the way it goes in one wavelength, and this is how often the wavelength passes every second, and so when lambda is high, the frequency has to be low, and vice versa. So blue light has a higher frequency than red light, okay, but only because it was then shown with this experiment that light behaves as a particle, because only blue light actually then emitted electrons when it hit the metal. So this gives us the relationship of energy and frequency, where h is the Planck's constant with a value of, I think, 6.6 times 10 to the negative 32 joule seconds. I'm not quite sure. I think this is how I remembered it. If I'm not, I'm going to correct myself. So, and basically this experiment has shown us that light behaves as a particle, because it doesn't matter how intense the light is, only the frequency matters. But the other experiment of Thomas Young has shown us clearly that light behaves as a wave. So what is it? Which experiment is wrong? Is any of them wrong? No. Both experiments are actually correct. And this led to quantum mechanics in the first place. Quantum mechanics, if you don't know what it means, I'm not going to explain the entirety of quantum mechanics. But quantum mechanics is basically just probabilities. But this drove Einstein pretty crazy, actually, because he couldn't believe that, in his own words, God played dice. But turns out that that's actually what God does. He plays dice. At least now I will not be recreating the photoelectric effect, but I can tell you how I would do it if I were to. Maybe I'll do it in a year or so, if I want to work with very dangerous metals that explode with water. So anyway, the singular energy of a red photon is about 1.77 electron volts, I think it is. Electron volts is a way to measure very small energies, like in the range of electrons, as the name already suggests. And blue light has about 2.76 electron volts. So basically I need a metal with a work function in between the two values. Now, what is a work function? A work function is basically the energy of a singular photon you need to kick out an electron out of the system. Okay, and the reason I need a metal with the work function being larger than the energy of red light but smaller than blue light is because then I can show that red light won't kick off electrons but blue light will. And basically there are two, or rather three, metals that come into question. One, cesium. It has a work function of about 1.9 electron volts. It is rather low, so it could work. Only problem is cesium is very reactive. Okay, and I could also use potassium, which has a work function of 2.3 electron volts, so it still sits comfortably between those two values. Only problem is that potassium explodes with water also. But then I could also use sodium, but sodium has a work function of 2.76, so it's way too close to blue light, because remember, blue light, as I said, has 2.76. Oh wait, excuse me, did I say? Okay, anyway, sodium has a work function of 2.75, and blue light approximately has 2.76, so no, I'm definitely not gonna be using sodium. Maybe rather UV light would be better, but yeah, I'm not gonna do it now anyway. So that's just basically how you could do it, or how I could do it, maybe a year or so. So I hope you liked that video, and if you do, you can like the video and subscribe. Bye.